So the Yukawa particle was Hideki Yukawa, and this is kind of an old-fashioned way to think about it. We now don't really, we sort of talk about gluons as being the force mediators, okay? But there is a way to think about it that we're mesons, and we're not going to really get into that too much. That a pi meson could be the mediator of the strong nuclear force. It is the least massive and most stable of the pions, right? But anyway, what Yukawa did was he said, look, if photons mediate the electromagnetic force, there has to be something that mediates the strong nuclear force, right? And you can do calculations with this. And the basic calculation is that, whoops, let's go backwards here. The basic calculation is this, is that the energy and the time, right, has got to be greater than or equal to h over 4 pi. Okay, well, the time is just the velocity divided by the distance, right? So the velocity is you can't go faster than the speed of light, and the distance is the diameter of the nucleus. So he threw in the diameter of the nucleus in there because the force has to be able to cross the nucleus, right? Threw that in there, figured out the energy, figured out it should be around 100 million electron volts, okay? And eventually they discovered it in cosmic rays. There's 3 charge states for a pion. But anyway, yeah, there we go. And this is one of our particles. This guy, by the way, is a meson, okay? And so these are the 4 forces of nature, and these are the particles that mediate it, right? So the strong nuclear force is mediated, we now say, by gluons, right? There is a model that people use where mesons actually mediate that force, right? Electromagnetic force is 100 times weaker, I guess, right? And it's mediated by photons. The weak nuclear force, which explains certain decays, like beta decays and that, is the W and the Z particle, okay? So these, by the way, these are fundamental particles, right? And the gravitational force, we know the relative strength. We have not yet detected a graviton. It will be exceedingly hard to detect because of the, it's not going to have a ton of energy. This is not a super strong force, okay? When we do detect it, we believe that it's going to be a gauge boson, but nobody wants to, we're not going to say that, right? More on that later, okay? So these are the 4 forces of nature, and these are the sort of fundamental particles that mediate it. So these are mediating particles, okay? And then when we look at particles and antiparticles, this gets a little bit tricky. So the general, my advice to you is just look them up. I'll give you a reference sheet for it. But for example, we know that the electron is the actual particle. The positron is the antiparticle of that, right? A proton, we use this notation, an antiproton, right? Sometimes, by the way, people say P plus and P minus, I don't know. Okay, a pion, you just have to look it up. The pi plus is the matter particle. The pi minus is the antimatter particle, okay? Some particles have no unique antiparticle, so what we say is that they are their own antiparticle. It's kind of like being your own worst enemy, right? Whenever you see pluses and minuses, those are charges, right? And there's 2 different notations for so by the way, we don't put pluses on protons, right? So you just got to know that's a plus, that this guy's a minus, right? Okay. So, it's a lot of it is just you got to know it. It's kind of like driving around Portland. When a particle meets an antiparticle, they actually will annihilate, which in the case of electrons and positrons, right, is that they actually turn into photons, okay? But other things annihilate differently, so you gotta, we're not gonna really go into that, okay? This is just a selected list of different particles. So here are our force mediators right here, okay? So the photon mediates the electromagnetic force. This is and by the way, we call these forces the electroweak force together, right? Leptons are fundamental particles, so all of these guys. And electron is the one we're familiar with, is the lepton that we're familiar with. All of these leptons, and there's 3 different types. Well, there's 6 different types, right? But there's one that has that is the main lepton, right? Okay, they all have their own neutrino that goes with them. Okay. And those all have their own antiparticles, right? So these are fundamental particles of the universe, right? The tau, a muon is just a fat electron, a tau is just a fat muon or whatever, right? Okay, these guys typically will decay into these guys. The electron is stable because lepton number is conserved, Okay, I'm just going to say, okay. So there it is, right? And then all of these guys are composite particles. These things are made of quarks. Okay, so mesons are quark, antiquark pairs. Baryons are quark, 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 and then the antibaryons are antiquark, antiquark, antiquark. Okay, so quarks are more fundamental, and these are not fundamental. Okay, this is one way to organize them. The other way to organize them are, and by the way, all these little pluses and minuses, those are just charges. And some of them, are like +2, +3 or something like that, right? The other way to organize these, by the way, is by their spin, okay? And spin is a measure, it's a quantum number. It's a measure of the angular momentum of a particle. And the smallest amount of spin is a half spin, which I think is spin is equal to Planck's constant over 4 pi or something like that. Okay, a whole spin I think is just h bar, which is Planck's constant over 2 pi. Okay, bosons have integer spin. Okay, and so gauge bosons, these guys here, have a spin of 1. There's one scalar boson, that is the Higgs boson. And we call it a scalar because it doesn't have any spin 0, right? Okay. And then mesons, all quarks have a spin of 1/2, okay? And so mesons, since they have 2 quarks in them each, are even number, right? They have an even number of spin 1/2 particles, right? Now, why this is important is that the physics of these 2 different particle groups are totally different. Bosons obey Bose-Einstein mechanics, right? And we're not going to get into that, but it's super cool. I mean, just look up. There's things like Bose-Einstein condensates. Superconductivity, I think, is a Bose-Einstein prediction, right? Okay. Fermions are non-integer spin, so by that I mean it's 1/2, 3/2, etc., right? Are non-integer. It's multiples of 1/2, right? These guys obey Fermi and Dirac mechanics, which the Pauli exclusion principle is part of that, right? So these guys cannot be in the same quantum state. These guys at cold temperatures will congregate in the same quantum state. These guys are no. Yeah, they cannot be in the same quantum state. That's what the Pauli exclusion principle was. So in chemistry class, when you filled in your little periodic table with spin up and spin down and all that stuff, right? That was the Pauli exclusion principle for that, right? So all of these guys, this guy is a fermion, fermion. What do we say? Okay, these guys are bosons, right? These guys are bosons. These guys are strongly interacting fermions. Okay, so just I don't know, maybe be able to tell me which one of these are fundamental, which one of these are made out of quarks, et cetera, et cetera. Maybe make flashcards. This is just sort of basic knowledge, right? This is somebody who made this great table here. This is kind of fun, right? So here's the Higgs, baby. We know, there it is, yeah. That's 2012, baby. That wasn't that long ago, right? Okay, so here's our scalar bosons. This is spin 0, right? These guys are spin 1. Right? And then all of these guys are spin 1/2, right? You can see the spin. Here's mass charge spin. All of these guys are spin 1/2. And then some of the composite particles made up of quarks, can be spin 1.5 or whatever, it just depends, right? Yeah. Anyway, so these guys, these quarks right here, okay, these guys make up mesons and baryons. Remember, mesons are quark, antiquark. And baryons are quark, quark, quark. It's so hard to do that, okay? I think that's all we need to do for this video, is just sort of, that's what type of particles we have.